south. This is, we can say that this is because of that track density here. If the, as in the tracking algorithm, we they did not get that density in the southern part as compared to the HV15. This is why this shift can should be there. And here the next picture shows that the here the blue one is 80 UGC track, median track, and the red one is for axis years, mean track, median track, and the green one is for deficit years. So here we can see that when the uh, it is axis year, then track is slightly shifted towards the north, but for the deficit year it is slightly shifted towards the south. But in the HV15, there is no significant shift in any of that. And for during the above and below normal, here we can see that during the above normal rainfall years, that shift is more as compared to the HV15. So here is the frequency for the LPS. So the this picture shows for the era 8, that for algorithm, and the second one is for HV15. So this algorithm is slightly less correlated with the frequency, as the correlation between these two is around 0.34. So it is not that efficient for the like getting the right frequency of LPS. So now these these low pressure is connected to the rainfall. So here they have plotted the mean track of median track of all LPS, and the rainfall during the like these contours shows the rainfall during the LPS days for both HB15 and 80 And here we can see that the most of the rain is during the LPS days. Most of the rain is along near the track, median track, and we can also see that the most of the rain is the south of the southwest of the track, as it is in the previous city shown that most of the rainfall occurs in the southwest part of the low pressure system. And here is the percentage rainfall for both ATAGC and HV15, that how much rainfall is occurs during the LPS and the whole rainfall days. So here we can clearly see that the most of the percentage lies in the central part of the India, as LPS gave as much rainfall in that region. And for the HB15, it is quite uniform in the whole India, in the except that south region. This is because due to the fact that HB15 got around 90 LPS days as compared to the ATAGC. ATAGC got around 68 LPS days per year. So here is the rainfall plot for the mainly LPS related rainfall. The for the rainfall, the the that in the radii between of 1000 kilometer of the track. So there is no much difference between HV15 and ATGC in for in that paper. They also show that how extreme events occurs during the LPS days. So the first figure shows that actually the extreme event is defined as the if the precipitation at any grid point is greater than 64.5 mm, then that point is called as extreme event point. So here we can see that the during the so here we first figure shows that the how many extreme events uh, occur during the whole period of the study. So here we can clearly see that the most of the extreme events are lies near the central region, which is mostly low pressure dominant, and there is also some uh, high frequency of the low extreme event on the Western Ghat. And here is the mean for every year, mean of annually, how many low pressure extreme event occurs. So mostly these two are similar, and the third picture shows that how the extreme event during the LPS days, ratio of LPS during the LPS days as compared to the whole extreme event. So we can clearly see that the percentage of extreme event during the LPS is higher in the central region. So I am trying to reproduce those results using ERA 5 data for that using that tracking algorithm. So I got and here I also calculate the genesis density that is quite similar as calculated by ATUGC using ERA interim data, and I also calculated the track density which is quite similar, and I also plotted the frequency that is not that consistent as compared to the ERA interim. So the conclusion is the LPS plays an important role in the rainfall for the eastern and central part of India, and that tracking algorithm used in that paper is correlated well with spatial distribution in terms of density or rainfall distribution, and but it is less correlated in terms of frequency, and precipitation within 1000 kilometer radii of ATAGC based on LPS tracks is found to be have a large correlation around 0.83, and 60-70% monsoon precipitation in the northern region is also found to be associated with LPS, and in the central region they found that around 82% of extreme events occurs during the LPS days. These are references. Thank you. Yes, sir.
Okay.
Yes.
Any questions? Anyone?
Comment.
Yes, sir.
Extreme rainfall threshold looks too low. That 64.5. That looks real too low for the extremes we see.
Yeah, actually,
Can you repeat the question because people may not hear?
Yeah.
You repeat the question and then answer.
Okay. So the question is the threshold for the extreme event is less as very less. So I think they did not mention why. I think they use that. But I don't know like in that paper they why they that threshold used.
64 mm per day or per hour?
It is accumulated for a day, that it at any grade point it is 64.5 mm, then it is extreme event per day actually.
As they calculate the speed of propagation of the low pressure system.
Is
Repeat the question.
Speed of the propagation of the low pressure system.
speed of the low pressure system, no, actually they did not calculate it in that paper the speed. They just use that algorithm. They how they used it actually, how they calculate is actually if they found a low pressure system in one time frame, and if in the next time frame the time frame is around between the gap is around 6 hours, if in the next time frame that low pressure system lies in the radius of around that 3 degree, then it is said that this is the same Celsius, then they use that track.
Anything from that? Everybody asking from there? Any chat box there? Indeed or not?
Chat box. No. No.
Okay. Thank you.
Thank you.
Your laptop?
Yes, sir.
Yeah, I'll put it there and see that I can.
Yes, sir.
Sorry.
Here.
There it is. Okay.
This is actually not here. Okay, here it is.
Okay. How is it visible here? This one?
It is in that.
This one?
This one, yeah.
Yeah. I just want to open it. Let's see if I don't use to it. Yeah, thank you.
Yes, I did.
That was slideshow mode. Oh,
Yeah. Yeah.
yeah. Why is it disappearing? Yeah, okay.
Thank you.
So thank Mahendra Singh for an interesting presentation on low pressure system. Now, if you look at what's going on in this year's monsoon, the data is still today, 6 July, and you can see we already got 213 millimeters of rainfall from 1st June, and it is close to normal, 213.3. So we are at 0% anomaly, which is quite good. Okay. Now, you look at the forecast made on 27 June, it's quite good, although numbers are not agreeing. I would say that the GFS forecast correctly predicted the intensity increase from 28 June to around 1st July, and then a slight decrease, and then a further increase in the last few days. So this indicates that the IT season is right over the Central Indian region, and it is quite strong. So up to around 15 July, this system will be around there. So the first half of July is looking good. Rainfall is, remember, Central India did not get much rainfall in June. So it is making up, and this is good news, because today it was 13 millimeters per day, which is 5 millimeters per day above the climatology. Now let's look at the status of the ocean. And if you look at the anomalies in Indian and Pacific, it has slightly changed, especially over India. Look at the warmer anomaly in the Arabian Sea. Okay, so this is interesting. Right in the northern Arabian Sea, you are close to half to 1 degree warming. I think, I do not know why, but I think it's partly because the ITCZ really did not move very far north in June. So the cooling that normally occurs with the Somali jet was not that much, I think. So you see the little warm patch there. But near the Somali coast, of course, there is a cooling due to the jet. So let's look at the Nino 3.4. The normal practice is to do a 3-month average. So in the 3-month average, you can see that April, May, June is still -1. Okay. So for the past 5 months, 3-month average, in this year, it has been essentially a strong La Nina. Okay, it's going to weaken a little bit, but still a strong La Nina. We look at the data from Bureau of Meteorology in Australia. The latest value is -0.3, but you must be careful. This weekly average sometimes misleads you. Okay? These are fluctuations which are normal in that region. So it's better to look at monthly or even a 3-month average. Don't get excited by weekly fluctuations. This is IOD. IOD is around -0.7. Now this to me is surprising. If you look at the SH anomaly map, it's not obvious that it's a positive, looks like a positive IOD. So Vinay, can you clarify why this is not consistent with that picture? Doesn't look like a negative IOD, right? Not yet. There's a slight hint of cooling near Somali Coast, that's it. But how is the negative valley coming? I don't know.
There is a warm anomaly patch in the western box. So probably that is
no, but that should give positive IOD, right?
Positive IOD.
Yeah, but the Bureau meteorology says negative IOD because it's a -0.7. Sorry, this one. It's -0.7 right now. I don't know how it came -0.7. So it's a bit puzzling how they got it.
Eastern box is positive.
Huh?
Eastern box, Eastern is right. That's positive.
But not very high. See, the color, another color scheme is wrong. It doesn't look that high. Maybe you should check with some other data set.
Those boxes are very high.
Huh?
Those boxes are very high.
Oh.
And you are seeing only one snapshot.
Okay. Yeah, now let's look at how the June 2022 is on the right compared to last year. Compared to last year, we're not doing well. Last year, the June rate was 182, this year is only 150. And you can also see that in June last year, the RTC had moved much further north. It went up to Indo-Gangetic Plain. This year, it did not. So it looked bad at the end of June, but in the first week of July, already this is up to 5th July, already things have changed. So you can see that July is a very important month for monsoon. If the RTC shifts rapidly, many of the red regions have become green. So this is what you want to watch for the next 1 week. Now this is a forecast by GFS for the next 4 weeks. You can see that GFS is saying that this week the system is well over the Indo-Gangetic Plain. Next week it will be slightly below that, anomaly will be more towards central India. Then there's a slight hint after July 15th of development of a break in the northeast region. But it is showing that in the last week, 4th week, it looks like it's not that strong. But as all of us know from the experience of watching this, we can only rely on the first two. First two is reliable. Next two, we are not sure. We'll have to, again, look at next week about this. Now, let's look at the forecast from GFS, the ensemble mean of GFS and European Center on the right. Okay. And you can see they are very similar. So this is interesting. For the first time, the forecast made by GFS and the European Center agree almost very similarly, except some regions over Pakistan. And the difference is GFS is showing a large negative anomaly over the, I would say, eastern Indo-Gangetic Plain and Bangladesh, while the European Center shows somewhat milder anomaly. So that's the only difference. Otherwise, they both say right in the central India, the rainfall continue to be above normal for the next up to 20th July. Okay. Now, what's MGO doing? MGO is right now favorable to us over India. You can see upper level divergence over India today. And this MGO is slightly going to move to the east and it will weaken in the week of 7th to 15th July. But the real question is beyond 15th July. Beyond 15th July, if the upper level convergence, which is in Africa, moves over India, the second half of July may be bad. Okay, so that is the only question mark right now. It depends on how fast MGO moves and comes over India, the upper level convergence. Now, I want to discuss the importance of July rainfall. Now, we saw last time that June rainfall has nothing to do with seasonal mean. It has no predictability. But July is very interesting. So I want you to look at, let me see if I get my pointer here. Oh. Yeah, this is too sensitive. Yeah, so if you look at this graph, you can see that June, July is the x-axis showing the summer, June, July rainfall. Y-axis is the seasonal mean, which is what our target is. And the blue line is the normal rainfall, okay? 890 or 880 millimeters right now. Okay, thank you. So, so 880 is our climatology, and 10% of that is right around 790 right here. So the key point I want to do, this figure, a very important figure, I'll keep repeating it, is that if the June to July rainfall is below 400, you are doomed. You're going to have a drought. Okay. So, so July is very critical. June was 150 millimeters. If July is about 250 millimeters, we will go over to this domain where probability of deficient but not drought, and even higher than normal is possible. But if you are to the left of this 400 millimeter line, you are completely gone. Okay. Now, interestingly, if is Pritham here? Okay, maybe he is online. So Pritham presented a work on the non-El Nino droughts. Okay, he looked at about 10 cases. Interestingly, all of them were here in this region. Okay, below 450 millimeters. So if you are above 450, the chances of a drought is very low. So the key target that should be looked at for the summer, June and July is 450 millimeters. So right now it is 213. We have 25 days more to go. If it averages 10 millimeters per day, you will get 460. Okay, so let's watch how it develops. We'll go to 460. The chances of this being normal is extremely high. There are only two examples in the last 120 years of below 790 millimeters. So I would say 98% chance of must be normal or even above normal. Okay. So this is a very important thing. As a matter of fact, I don't know, and this is purely from data. What is the reason? Why, if the June rainfall is above 450 or 460, why is that normal is guaranteed? What it means is that once June rainfall is above normal is 460, is above normal, then there is enough soil moisture in the Indian land that the water vapor in the atmosphere above the land is sufficiently high to promote convection. Okay. On the other hand, if the June-July rainfall is below 400 millimeters, the soil becomes drier and will cause the water vapor to decline, and that will suppress convection. So what happens in the first 2 months of the monsoon is very critical. And so this result, I'm not sure is highlighted well. So it's a very important forecasting capability that if the June-July rainfall exceeded 450, 460, there's 95% chance that the monsoon will be normal this year. So I think this year is going in that direction. But remember, it has to rain average 10 millimeters per day for the next 25 days. That is the target. So from what you have seen so far, it will happen for the next 1 week, no problem. The question is beyond 15 July. So next week we will watch what is happening. If it falls into this domain, then you are in deep trouble. For example, right now 230, it only rains 200 millimeters, then you're somewhere here. So your chance of drought are more. But if you move into this domain, you are. So this is interesting result, which purely based on past data, but I have not yet seen anybody talk about any mechanism which can explain why this happens. Now, this is a performance chart given by India Met Department. It's not easily accessible, that's why I'll show it to you. They're comparing the last 5 years, last 6 years here. Around the last week of June or first of July, okay? This is every Wednesday they put it out. So wherever the last Wednesday comes, they put it. You can see that all India departure this year is minus 10%, similar to 2018, but better than 2019. 2019 was minus 36, but remember 2019 was a very unusual year. It was minus 36% on 26 June, but it was well above normal at the end of the season. So 2019 is a very unusual year. Yes? this is already department, usual ISMR. These are number of subdivisions which are our number now. Up to here it is the subdivision number can add up to 36. Okay, but this is the all India rainfall number. Okay, there are other graphs showing the percentage of the divisions which are that are not shown. So what I'm saying is that this year not bad compared to, but not as good as last year. Last year, as you saw, was much better. But compared to 2019, we are doing much better. But even 2019, in spite of such a poor situation, it recovered. So that possibility is always there in the case of monsoon in July and August. Yes.
In 2019, it was the last week of September.
September
was one big.
I know. 2019 is the most unusual. Even today, we don't have an explanation how 2019. But sometime maybe Arindam can talk about it. Arindam has some ability to forecast that. How September was well above normal. Yeah. That's partly because I think 2019 the La Nina came very rapidly. Am I right? That is the key. So that is the issue. What happens? Not the present La Nina state, but the date of change. So that Arindam wrote a paper some time ago about how not only you should know the present state of 3.4, but how it evolved from January to now. Okay. I think that also plays a role, and that's I don't know the map. I just want to show the one-day forecast just for curiosity. You don't see it often. One-day forecast is pretty good. This is one-day forecast from 4th July, what happened 5th July, shows rainfall occurring over the Nagpur region, and so does the observation. So one-day forecast, of course, is now absolutely excellent. Now, to end this talk, I just want to talk about the role water vapor plays in the Indian monsoon. Now, to illustrate its importance, we still don't know how it does because there are a lot of feedbacks going back and forth. One cannot separate out those things. But if you are willing to look at hourly data, we see a lot of very interesting insights which is important to learn. This is data from Neelan, who looked at rainfall from a radar in the West Pacific. There's a well-known radar there. West Pacific as a part of the campaign US conducts there. And so what you have is on the x-axis the lag, okay? And this is the amount of water vapor, okay, with respect to rainfall here. So what this shows very clearly is hourly data. However, has increased from 50 kg meter square. Oh, sorry. How do I get rid of that? Yeah. So 50 kg per meter square, and it goes up to around 53, 54. Then the rainfall really picks up rapidly. And after rainfall picks up, the water vapor goes up even higher. So water vapor has two things happen. There is a requirement of water vapor to go up before rainfall can occur. Once the rainfall occurs, the rain droplets evaporating on its way down increase water vapor further. So it's a complicated feedback. You require more water vapor to increase rainfall, and once water vapor rainfall occurs, water goes up further. So this all in matter of a few hours. You can see that this is 12 hours, no 12 hours later. So the change, 50% of the increase occurs before rainfall, 50% occurs after rainfall. Okay. This is a very interesting insight, but it's hourly data, of course. So we cannot easily translate this to what's happening on a weekly, monthly scale. But this shows you why water vapor and rainfalls are so intimately coupled. One affects the other. Okay. And this was shown by Neelan in a very nice result published again from this data. X-axis is column water vapor, y-axis is rainfall, and those colored lines are column mean temperature. So this is the first result, again observation, which clearly demonstrates, anyway, the first order is a alumni of this COS, Sani, and what it shows clearly that for a given water vapor, you may get no rain even at 60 kg per meter square if the temperature of the column is 274 Kelvin. Okay, that is around 234 is 20. Sorry, it's about, column is only about 1 degree above 0 degree centigrade. Now, from 234 goes to 269, just 5 degrees decrease. See how much rain increases. So this shows how sensitive the rainfall is dependent on the column temperature. Now, this is something is not highlighted by many people. Now, people talk about the impact of water circulation, Hadley, and so on. All that is not required. What happens during El Nino events, for example, is because of unusual amount of rainfall in the Pacific, equatorial Pacific, the whole column warms up, and since in the tropics, pressure waves travel east-west and equilibrate everything very quickly because the pressure was very low. So in the tropics, within a matter of weeks, the warming of the column over the Western Pacific, normally, that's where the real heat source is, travels across right around the world, and all the places column temperature goes up. If it goes up, you can see how rapidly the rainfall declines for the same amount of water vapor. Okay, so this is a fact not sufficiently appreciated, the important role played by warming of the troposphere for a given amount of water vapor. Okay. This is only, of course, a diagnostic thing, but I think this partly explains why during El Nino years, when the troposphere warms a lot, your rainfall comes down, and in a La Nina year, there is not enough heating, the troposphere cools, you get more rain for the same water vapor. Okay, that is the key message from this very nice graph. Okay, I'll stop here. Last time I showed this picture, and Professor Venu made a remark which was relevant, that this part of the figure is obvious. When both June, July, and August, September are below normal, of course, we get drought. But the question that is not clear is, when the June, July, August rainfall is above normal, there is no chance that August, September will be so much below normal as to make the all India rainfall well below normal. So that's the part which is still not fully explained. This part is very easy, because both the early part, late part are below normal. Of course, the all India rainfall still may be below normal. Okay, I'll stop here, and any questions, you're welcome. Yeah.
Can you go to the slide?
Yeah, remove your, I can't hear.
Go to the slide where you showed hourly.
Yeah, I'll show that.
Yeah.
This one, yeah.
Yeah. So the rate of increase of column water vapor before the rainfall and after the rainfall are different.
Yes, you are right. That's not surprising, right?
Yeah.
Because before the rain, the column water increased due to advection or convergence, something. But once the rain occurs, the liquid droplets will evaporate rapidly. So it will evaporate very rapidly. Okay? There's no question about that.
Yeah.
But this is quantitative. See, many of these things are known qualitatively to any synoptic meteorologist. Okay, but the real data was obtained by Neelan from that one website. I wish we had one in India, a good website, a good location where we measure water vapor and rainfall simultaneously on an hourly basis. Then you will get a real insight as to what's happening to that. Yeah, the slope is very different. That's a very sharp slope after rainfall onset.
Do you think?
But remember, but the total change is not very different. I would say before rain it goes up from 50 to 53, after rain 53 to 57. So the amount of change is not, it is the rate of change, you're right. Yeah.
So do you think we can see a similar result in reanalysis data if we get hourly data for reanalysis?
Please check it. Yeah, it's a very good point. Please check it, because I'm very skeptical about reanalysis. I would suggest please compare with ERA and NSEP and maybe Japanese, and if it is not coming out right, publish a paper. Okay, because we all trust reanalysis a lot, but when it comes to water vapor and rainfall, especially rainfall, I tell you, is pretty shaky. But please check it. It's a very good point. Somebody should have done it. Maybe they have done it. I don't know. As a matter of fact, you should send an email to Sani and ask him. He may have done it. Okay. Ravi, Sani is in Singapore now, right? He's not in Delhi. Yeah, you can get his email. Please send the email to him and check whether this is consistent with real answers or not. It's a good question.
Yes, it's
I know, but if it is properly, see today in weather forecasting, you are assuming a lot of water vapor. Okay, the water vapor will be right, I'm sure, but rainfall you're right.
Rainfall. So
Rainfall.
the second part of it might be.
Yeah, but I think that it could be, if it is not good, it's worth knowing. To me, suppose whatever does go up, but rainfall doesn't, rainfall not here in this picture, by the way. It's only showing how whatever it is before and after. So it may be okay. Because rainfall itself is not shown here. No. It's only the rate of change of water vapor before and after rain. Okay? So you have to read the paper and see carefully how they did it. And the same thing you have to do it with the rain also. But I think it's worth looking at. Because yes, Ravi is right, rainfall may be wrong, but we are only asking this question after, I'm sure, I don't know what rainfall they use as a criteria. After rainfall above a certain amount, look at the water vapor before and after. That's all they're saying. Yeah. Anyone else? Okay. Is there anybody check? Anybody asking question on the branches? Is anybody? So far, not any question. Yeah. No, this one. No.
Depending on temperature on this water vapor. Right? So can you explain this graph once again? Like role of.
No, this graph is based on the idea of understanding what controls rainfall for a given water vapor. Okay, and this is a parcel theory idea. You have a parcel which has to go up, right? And if the parcel temperature is higher than the ambient, it will go up much faster, right? So the question is, for the same amount of water vapor, if the troposphere is warmer, the parcel won't go up that much. That is the whole idea here. But this is from observation. That's all the difference. So parcel theory will satisfy this totally, but this is the first time somebody has taken data at very high resolution at hourly scale, same as the other graph, and actually plotted the mean temperature in the troposphere and water vapor, showing what I like about this result. Please notice very large difference. Again, I want to repeat, at 60 millimeter water vapor, which is very high, there's no rainfall if the column is very warm. Okay. For the same amount of water vapor, you get 5 millimeters per hour. Remember, there's a millimeters per hour. Okay. So there's a huge effect. And somehow this is not sufficiently highlighted by any other papers I've seen. Okay? Of course, Dylan has published many papers. Please look at all of them. And he has a chapter in a book, which you should read that. So this to me is to be understood in the El Nino La Nina framework. In the case of La Nina, temperature of the column will be 1 or 2 degrees colder. In the case of El Nino, it will be 1 or 2 degrees warmer. There will be huge difference in rainfall just because of that. Okay? So again, I would welcome all of you to look at reanalysis. Please look at the column mean temperature in El Nino year, La Nina year, in various parts of the world. You will see whether this is true or not. Although I want to warn you, this is all hourly data, and normally we look at weekly, monthly, and seasonal. But I think you can learn a lot by looking at hourly data. So reanalysis is there. It's worth looking at reanalysis also, getting this correctly. Okay. Okay. Thank you. So next week is Sujatra, right? Yeah. Okay. We'll meet next week. We'll continue here, but please check with the people whether the reception is good. Okay, let's get a feedback. We'll continue, and I hope very quickly the new laptop will come. Thank you.